My project is mycelium growth modeling using artificial intelligence-based image analysis and complex network theory. The mycelium and the network it formed has many functions, like grasping the nutrient, transferring signal. Also, mycelium has a lot of physical properties like strong compression resistance and ductility, which has been developed for packaging and decoration. In this project, we focus on the following objectives. First, segment mycelium images to obtain mycelium network graphs using hybrid manual and machine learning algorithm. Then, we calculate fractal morphology and complex network indicators of mycelium network graph. Last, we try to relate growth of mycelium with fractal and network morphologies over time. This project revolves three main problems. First is about exploration of methods for network extraction. Second is to determine the network indicators which can reflect the mycelium network graph accurately. Last is how to interpret these values and relate it with mycelium growth over time. There are two parts in my methodology. First is about image analysis, including image pre-processing, image segmentation, and network extraction. After that, we can analyze the characteristics of the network graph by fractal analysis, construct adjacency matrix and Laplacian matrix. Reviewing the literatures, the interactions within cells of mycelium has been investigated widely. As for the image analysis, we can obtain many methods in biomedical field, like tumor diagnosis, which requires image segmentation to discriminate the abnormal part from the healthy part. Also, we review the study of fractal analysis and complex network analysis. Fractal analysis is widely used for explore the morphology of objective like snowflake, nanoparticles clustering, even used in the curve of stock market. Network analysis, no doubt that it can be seen in every field related to network structure, especially in social science and economy. However, the study of the morphology of mycelium network is fewer than on the biological process. Meanwhile, AI-based image segmentation methods, including machine learning and deep learning, have been significantly developed in the biomedical field. The segmentation techniques for mycelium networks remain undeveloped and lacking in sophistication. Some researchers have focused on studying the static features of mycelium network, but there is a limited amount of research addressing the dynamic growth of mycelium. The left side is the raw images that look blurred, and many features of mycelium are hidden due to the uneven pixel distribution. After contrast enhancement, gamma correction, median filter, there is a better contrast between objective and background. Contrast enhancement can help broaden the gap between different pixels. Gamma correction can adjust the brightness, and the median filter can filter some noise. Then we want to segment the images. The first step for image segmentation is to extract the features of our images. There are plug-in functions in Fiji for feature extraction. For example, Sobo filter can detect the edges in the images, and Hessian matrix can detect the ridges in images. After these algorithms, we can build up a feature matrix. Y is the result that we can determine it is foreground or background by leveraging the features. The AI method that we use is random forest. The first image is the overall flow of random forest algorithm. First step is to start with an empty tree. Then select a feature to split data. For each split of the tree, we will determine to continue splitting or stop and make predictions. We can see the second image that shows a more detailed how splitting conducted. Started with data M, we use one feature to split. The data M will be separated into several subsets. Comparing with choose label, that we can calculate the classification error. We want to seek the minimal classification error to split the data M. After that, the following subset will operate the similar process to determine the best feature to split their own subset. The specific process of random forest can be achieved in the plugin function WEKA in the Fiji. Look at the interface. We first choose some typical area of mycelium as class 1 and choose typical area of background as class 2. The selected areas are the training data to obtain feature metrics. Based on that, we then do the global segmentation. Here is the results of segmentation. The top one is the segmentation based on AutoSU method, which is a segmentation based on a global threshold value calculated by AutoSU algorithm. The bottom image is the result obtained from AI-based method. There's no doubt that the bottom images exhibit more details, but there is still some challenges. That the method based on random forest still cannot detect some very tiny details. So therefore, we need to tune the images, deleting or adding some lines manually. Using skeletonization algorithm, we obtain the skeleton of the mycelium. Then we leverage the ridge detection to obtain the junctions and edges of mycelium network graph. We can adjust the parameters to achieve the ridge detection more precisely. The sigma parameter determines the scale at which you want to detect the ridges. Specifically, it controls the size of the structures we are trying to identify in the image. A large sigma value will result in the detection of large structures, while a small sigma value will focus on smaller structures. For minimum and maximum length, this defines the acceptable range of lengths for detected ridges. Ridges that fall within this length range are retained, while others are discarded. Next, we begin to network analysis. First, we compute fractal dimension by fractlag, which is a plug function in Fiji. The diffusion limited aggregation model takes shape by integrating Brownian motion with a fractal dimension of 1.5 to 1.7. When the fractal dimension reaches 2, it signifies a structure formed entirely through random process. So we want to relate the fractal dimension of mycelium to DLA model. Diffusion limited aggregation is the process whereby particles undergoing a random walk due to Brownian motion cluster together to form aggregates of such particles, which leads to an intricate fractal. When diffusion occurs more slowly than aggregation, it leads to the formation of an aggregate with a branched tree-like structure. This kind of structure is characteristic of the diffusion limited aggregation universality class. Conversely, if diffusion happens faster than aggregation, it results in the formation of a compact spherical structure. This compact spherical growth pattern belongs to the Eden universality class. The results are listed in the table. There's no doubt that the fractal dimension of mycelium is increased over time due to the mycelium expansion, but it seems at early stage mycelium growth do not match with the DLA model precisely. From Fiji, we also obtain some basic morphological values of mycelium, like density, width of bonding rectangular, height of bonding rectangular, diameter of bonding circle. There's no doubt that mycelium becomes more complicated over time, but there is a value that we can notate is the density. The density at the stage of 72 hour is smaller than the density at the stage of 48 hour. This may be because that mycelium in this stage prefer to expand outwardly, so the density may become more smaller. The software Fiji can generate a table containing contour 1, contour 2, and the position of junctions X and Y. Using Python, we can modify the table and obtain the junctions with label 1, 2, 3, etc. Now we have the junctions and the contour, so we can obtain the adjacency matrix. If two junctions have connected, we represent it by number 1. If no connection, use 0 to represent it. Using MATLAB, we can simulate the mycelium growth from 48 hours to 96 hours. No doubt that with time growth, mycelium expand rapidly. Based on the adjacency matrix, we can compute some common indicators like network entropy, average clustering coefficient, degree distribution, and the robustness of network. Look at the network entropy. Low entropy values often correspond to networks with more uniform distributions of nodes and edges, indicating a certain degree of homogeneity or regularity. Conversely, high entropy values signify more diverse distribution, highlighting heterogeneity or randomness. Besides, a high average clustering coefficient suggests that nodes in the network are more likely to form groups or clusters, indicating a higher level of local connectivity. On the other hand, a lower average clustering coefficient implies that nodes are less likely to form such local clusters, and the network might be more random or less structured. As for the degree distribution, we can see from the plot that it is kind of like bell shape, and the degree variances are moderately large. Last is the robustness that we can see. Even in the early stage, mycelium also has a strong node removal robustness. In practical terms, this implies that even in the event of the removal of a substantial number of nodes, the network's core structure and connectivity are more likely to remain intact and less susceptible to disruption. To sum up, the mycelium network demonstrates several notable characteristics. It exhibits a low average clustering coefficient and degree distribution variance, along with higher network entropy and node robustness, all while displaying a distinctive bell-shaped degree distribution. These findings suggest that the mycelium network shares some similarities with random graphs, making it well suitable for efficient nutrient search and absorption. However, it's important to acknowledge that the precision of these values may be affected by the limited observation time, making it challenging to determine the exact level of errors associated with these conclusions. Based on adjacency matrix, we can obtain the Laplacian matrix. The diagonal values of the Laplacian matrix represent the degree of each node in the graph. The off-diagonal values represent the relationships between nodes. A non-zero value between nodes I and j indicates that there is an edge connecting those nodes. The magnitude of the value could be -1, which means there is an edge, or 0, which means there is no edge. By leveraging the equation, we can obtain the eigenvalues of Laplacian matrix. The collection of eigenvalues is referred to as the spectrum of the graph, and the number of times an eigenvalue lambda appears is termed its algebraic multiplicity. The number of zero eigenvalues or values close to 0 corresponds to the number of connected components in the graph. There's one zero eigenvalue at the stage of 72 hours, while no zero eigenvalues at the stage of 48 and 96. If it has only one connected component, meaning that there is a path between any pair of nodes in the graph. If there are no connected components in a graph, it means that the entire graph is a single connected component. In other words, there is a path between every pair of nodes in the graph, and there are no isolated or disconnected subgraphs within it. We also have the eigenvectors of Laplacian matrix. In clustering analysis, especially in the spectral clustering, the smallest eigenvector offers crucial insights into the underlying data structure. Utilizing the information from the three smallest eigenvectors, we conduct network clustering and extract the primary network structure. Based on the eigenvectors and we partition mycelium network into three groups, we found that mycelium growth exhibits similarity at the 48-hour and 72-hour stages, while at the 96-hour stage it displays a distinct structure compared to the 72 and 48-hour stages. This indicates that mycelium would tend to expand outward and connect it closely in the next stage, with the central region becoming intricately entangled as it grows, which reflects the decentralized features. Generally speaking, this project constructs a protocol by using Fiji for image analysis from image segmentation to network extraction. Also, we develop the codes for the computation of fundamental network metrics, encompassing the calculation of the adjacency matrix, network entropy, degree distribution, average clustering coefficient, node removal robustness. Besides, we simulate the mycelium growth by adjacency matrix and partition the mycelium network by Laplacian matrix. We found that mycelium grows rapidly and shows some features of random graph. By leveraging the eigenvectors, we find that the networks at 48 and 72 hours are isomorphic, while the network at 96 hours showed a different structure. There are some limitations. Foremost is the sensitivity of ridge detection to image noise, where even slight noise can lead to false positive and inaccuracies during ridge identification. Consequently, effectively addressing a diverse range of ridge structures using a single method remains a significant challenge in this project. Furthermore, given the intricacies of mycelium growth within complex environmental conditions, batch image segmentation becomes challenging because of the variability in the outcomes across images. In this project, we only work with a single set of images, which limits our ability to analyze the errors in the network indicators. Another aspect is the mycelium objective itself. The mycelium grows from 24-hour to 96-hour is constrained by an incomplete pattern formation, resulting in a deficiency of key essential characteristics. For instance, the DOA model is unclear, despite the fractal dimension falling within the range of 1.5 to 1.7. Besides, the clarity of the degree distribution and the emergence of communities tend to improve as the network undergoes more mature growth. So the future work includes the exploration of ridge detection algorithm or other edge detection methods tailored to mycelium analysis. This endeavor necessitates a deeper understanding of mycelium image characteristics and geometry. Building up image dataset and the application of deep learning techniques for image segmentation are on our agenda to obtain more precise results. We can only train our algorithm and develop our protocol once we have gathered a sufficient amount of data. And we need to revise the technique to monitor the growth of mycelium and capture clearer and more consistent images. Besides, prolonged monitoring of mycelium growth is necessary with an aim to illustrate the characteristics of a more intricate and fully formed mycelium pattern. This may yield a clearer DOA behavior in mycelium growth. Moreover, we are keen on investigating the network features as mycelium matures into a more elaborate pattern and exploring any variations and outcomes under diverse growth conditions, along with their interactions with the surrounding environment. On a micro scale, the investigation into how nutrients and signaling substances propagate within the mycelium network represents a pragmatic study, one that has the potential to contribute to development of biological computers and innovative solutions in fields such as biotechnology, agriculture, and environmental science. To conclude, from the value of a fractal dimension, the mycelium growth doesn't show an evident feature of a diffusion-limited aggregation model at the early stage. From the static indicators of a network graph, there were some features of random graph showing that in the early stage, random walk graphs often exhibit the small world property where most nodes can be reached from any other node in a small number of steps. This implies short average path lengths between nodes, facilitating efficient information flow and navigation. Mycelium is typically well connected, meaning that there are usually no isolated components or disconnected nodes. This could suggest that information, signals, or processes can separate relatively easily across the entire network. We observed a different structure between 96 stage and the previous stage by leveraging spectral clustering method. Our research finds that mycelium would tend to expand outward in the next stage, with the central region becoming intricately entangled as it grows, reflecting the decentralized features. Nevertheless, the challenges in ridge detection persist, encompassing issues such as over-detection and omit detection. Furthermore, due to time constraints, certain features of mycelium, such as the fractal dimension, degree distribution, and community structures, may not exhibit distinct characteristics. Addressing this problems and refining our methodology is an essential part of our ongoing research efforts. Thank you.